Here we are once again. In tonight's video, we will deal with digital electronics, and specifically with gates. Let's move away a bit from analog electronics. Let's talk a little about the design of digital circuits. I will tell you two things about Boole functions, how we can simplify them with the Carnot map, how from there we can create an age map, and finally a complete circuit with gates. I don't know if what I said sounded like Chinese to you, but in order to still be here, you must be interested. And in order not to miss the next videos, subscribe to my channel and hit the notification bell to receive the new videos immediately. Now let's get to know the basic gates, the three basic gates and their truth tables. It's the AND, the OR, and the NOT. I will now draw them on paper one by one so you can see how the truth table is depicted and the function bird that each one has. We start with Ant, where X is her income, can only take the non-zero and 1, and F is her output, which is also 0 or 1. We say 1 when there is some bias in the output, and 0 when there is no bias. The same goes for the inputs. And what do we observe? We observe here that only when I have both x1 and p1, it gives us output 1. That is, I must have a signal in both x and s in order to give us output 1. It seems that its output will be a movement, a multiplication of the two inputs. That is, in the first case, I have 0x0x0, in the second 0x0 to the third 1x0 row, and the fourth 1x1x1, where of course is ant x1x0. That makes us 0. 0x1x0, and finally 1x1x1, 1x1x1, and the feed is a function f equals x, that is to say. And from now on, whenever we see in an x function, we'll have in mind that we have an ant portal. This is symbolic. Let's go to the next gate. Or I draw it here and we see that its results, it's like adding, hence its function is x plus. Observe in table number that only in the last piece, that is, 1 and 1 had to do 2. But in digital we only have 0 and 1, so makes us 1. This is the only difference with mathematics. And from here on out, if in a function we see x plus in, we will, if we see the plus i's, we think straight ahead that there is a portal or... And finally we have the NOT gate. None from a inverter. It has an input and an output. And if we give 0 at the entrance, the output 1 will give us the output 1. And if we give to entry 1, its exit will give 0. And on top of a function b, we will find it as a tone. That is, on top of an x, new tone is a reversed x. So we will talk about these gates. With these gates, we will make our circuits. There are enough 3 gates to create circuits. Combination of these and suppression of functions b, and in order to understand it, let's see an example. So to build a circuit, what do we need? We need the truth table or the output b of the circuit. And from there on, we will try to bring it to a state that will have the fewest gates above. Let's put it that way, in order to be able to construct it easily. Let's now see from a truth table how we can find an equation b. And I will start from a known truth table of the gate omega, and I will show you how we can also simplify to reach the desired result. In this particular case, we have 2 variables, one output and... To say here that interest us to build b, we are only interested in the output with 1. And where we see 0, we will emphasize x or y where it finds 0, and in the end we will calculate a sum which will be b. So let's do it a bit to see it practically. Here in these 3 cases we have an output of 1, so we will create 3 sums with the first one being seen over here. X is located at 0, so what we do above, we emphasize it where 0 we emphasize, and piece is at 1, so we leave it as it is, x times pa. We found the first product Let's go to the second. Here we see x is 1, we leave it as it is, p is 0, we emphasize it. Second product. Let's go to the third, sx and p remain as they are. This is our output bool, the bool of exit. Our function, that is f. So my exit is all this here. You see, it doesn't look at all like the OR we learned before. What did we say before? That OR is f equal to x or piece. This is what we had to find. And yet is the same circuit, that is the top and bottom one, give us the same result. If we build the same circuits with gates, the result will be the same at its output. We just said we haven't simplified it now, that's why such a large function comes out. And we will need more gates to create the same result. What we said before, that we need to simplify it in order to be able to build a correct circuit. So observe the bottom circuit for a moment. What do you see? I see 1, 2, 3 AND gates, which feed into an OR gate at the end. That's what I see now in the second function. While in the first one, we see one OR gate. There are many ways to reach from one state to another, that is, to simplify it. I prefer the Carnot chart and not the other Ergampool, but I will show you this in another video, how simplification is done. Now I will make the two little circuits for you. I will draw them on paper for you to see how it's done. The same circuit, two cases, to gradually get into the logic of design. With these little things we have found so far. So in the function I see two inputs, x and p, and three products, which are the three AND gates. I will make them here, 1, 2, 3. The first one, what happens here? What does the function tell us? The first one takes the inverted x, that is. So I will invert the x here with a NOT gate. Where we said it does this thing, I will put a NOT gate here, and I will give one input to the first gate ANT, and the psi takes it as it is, and I will also give input the psi. We finished the first ANT. Let's move on to the second. First we will create the products, so she tells us we take input x, and in the second input we see inverted input y. So we put another NOT over here, a NOT gate. We invert and send the inverted input y to the second ANT, and we move to the third. She tells us that she takes x and y normally without inversion, so we give input x. Let me take it from here, x input, and we will place the p above here at the entrance. Okay, and now we will add the 3 additions. By gates, I want to say now that they do not have only 2 inputs. They can have multiple inputs as well. So they can create one with 3 inputs, one or gate with 3 inputs. To make my addition, so I'm designing an OR gate here, which takes the 3 inputs from ANT, from the 3 ANT, and gives us the output, which is F. Here is the output that my circuit will give me, which is none other than the truth table of an OR that we mentioned before. This here will give us, that is, in my output, depending on what x and y will give, the input F will give us the truth table OR. And now we said that this circuit OR, what we made, is equal, an OR gate with 2 inputs. X and Y and output F, the same little circuit. We now observe that without simplification, you see how many gates we need more to make one. The better simplification we do in our gate, we will use fewer gates to build a circuit. So those of you who are here today, I want you to watch the video a little to understand a little of what they said. If you have any questions, write them to me. any comments you have and I can answer. In the next videos, I will also tell you the truth table. I will tell you how we go from truth table to function and vice versa until we build a whole circuit. Well, take care. Thank you very much. Hello to everyone.